computer, and here we go. So hello everyone. This is part of our class meeting for Tuesday, October 27th. And we've already done some last questions on the 4.3 DA that's due tonight. And we have talked about how binomial distributions look like normal distributions if the sample size is big enough. And we're about to go into section 5.1, variability in estimates. So I've asked if somebody wanted to share their screen. I've not really heard anybody for that. So I'll go ahead and share the screen, and we'll do some stuff again that is already there with the slides and screencasts for you to look at on your own. But I'll try to throw in slightly different emphasis so that those of you who are here or who watch this screencast later can get more points of view on it. So, sharing screen, desktop, share. Okay. So you're going to need Tiger Stats, or I am, and I've got that loaded. So I need to give you some definitions to set up what's going to happen in this chapter. And this is going to apply for the whole rest of the course. We're going to be a situation where we're going to be taking samples out of a population. And we're taking the sample because we want to know stuff about the population. And quite often what we want to know is numbers that are associated with the population. A parameter is any number that's associated with a population. Now, the parameter is not going to depend on chance or anything like that. It's not a random variable. It's just this fixed number associated with the population. We'll see some examples in a minute of parameters. It's a fixed thing, but because it depends on the population and we don't know everything in the population, then we're probably not going to know that parameter. But it's something that we wish we knew. And so that's why we take samples from populations. We use samples to try to figure out roughly what these parameters might be. When we take a sample, we know all the data in our sample, and so we can compute numbers from the sample data. Any number that you compute off of your sample data is called a statistic. That's why this subject is called statistics, because it examines the behavior of statistics. Now, a statistic is something that you'll know because you've got your data. But the other thing is the statistic is a random variable. It's a number that depends on the data, but the data depends on chance for how the sample was drawn from the population. So it's a number that depends on chance. So it is a random variable. A different sample would have yielded a different statistic. So you can know it, but it could have been something different if you'd had a different sample. And the name of the game is that you're going to use a statistic to estimate a parameter. Here's some examples of parameters. One example is the mean of a population. Mu is the Greek letter for mean. That's a number associated with population. If you have a population of people and everybody has a height in a population, and you add up the heights and you divide by how many people there are in that population, that would be a number associated with the population. It would be the mean height of all the people in the population. So that might be my mu. And if you wanted to know mu, well, you're kind of out of luck because you can't know the entire population. It's too big, but you could take a sample and you could take the mean of your sample. That's called X bar here. And you would use that sample mean, X bar, to estimate the population mean, mu. Or the standard deviation of a population could be estimated from the standard deviation of your sample. Or the median of a population could be estimated from the median of your sample. the third quartile of a population could be estimated from the third quartile of your sample. And I could go on and on like that with examples of parameters that could be estimated from statistics. And these statistics are often called point estimates. They're called point estimates because they're one number, and they're called estimates because we know they probably aren't going to be exactly equal to the parameters they're trying to estimate. They're going to be a little off. But we're hoping they're not too far off. So we're hoping that usually the point estimate is going to be approximately the same as the parameter. There are 5 basic parameters that we're going to be working with in future chapters. Now, I'll kind of give you a brief rundown of each one here. Like in that average height of all people in the population, that's when you're interested in one population mean. And you'd estimate it with the sample mean from your sample. But there's also situations where you might be interested in a population proportion. Like say you wanted to know the percentage of people, the percentage of all registered voters who are going to vote for Donald Trump, you know. Then you think about people in the population, everybody in the population is either going to vote for Trump or not, you know, kind of a yes-no thing about the person. And if you counted up all the people who are going to vote for Trump and divided by the number of people, you would have a proportion. The proportion of all people in the population who will vote for Trump. That's one population proportion, and it's called little p. So you got to kind of watch out here. There's a little p in binomial random variables, chance of success on each trial, and there's a little p that's one population proportion. Well, you would estimate that by taking a sample of people and asking everybody in your sample, are you going to vote for Trump or not? And you count up how many people say yes, and you divide by the number of people in your sample. And that would be a sample proportion, and it's called P with a little hat on it, P hat. It's also possible you might want to compare 2 population means. Like you might want to know like, I don't know, is the GPA of students at University of Kentucky the same or different on average as the GPA of students at Georgetown College? So you got 2 populations, all UK students, all Georgetown College students, and you got 2 means, like the mean of the UK students and the mean of the Georgetown College students, and maybe you're interested in just the difference of those 2 means. So you might estimate that by taking 2 samples, one from UK and another from Georgetown, computing the sample average for each one and just subtracting them. Or maybe you're interested in like, are women more likely to vote for Biden than men are? And so you got 2 population, all women, all men. And maybe you've got like a proportion of all women who are going to vote for Biden, maybe that's called P1 here, and a proportion of all men who are going to vote for Biden, P2. And you're really interested in the difference. And so what you might do is you might take a big sample of men and a sample of women. And the sample of men, you would compute, you know, the proportion who vote for Biden, and for the women, you compute the proportion who vote for Biden, and you subtract those 2 sample proportions. It's also possible that you got one population in mind, but you have 2 numbers for each person in the population. Like maybe, like what if you could make everybody in the population go on a certain special diet? And you record their weight before they go on the diet and then after they're done with the diet. So 2 weights. And you might be interested in like, do they lose weight when they're on the diet? So you'd be interested in like the difference in the weights. And so you could take the difference for everybody and average that up. And that would be called mu D here. Well, you could estimate that by just using a sample of people and putting that people in a sample on the diet. and you record before and after, and for each person you subtract and you have a difference and you average those differences. So those 5 situations are ones that we're going to talk about a lot for the rest of the course. But in this chapter, we're really gonna work mostly, we'll work mostly with one proportion, you know, but they try in this section to give you some practice in talking about a practical scenario and figuring out which of these possibilities you're actually interested in. They're not going to do much with mean of differences in this chapter. When you read the book, you see that they don't. The main thing that they want you to know in this section is like, when are you interested in one mean versus when you're interested in one proportion. So I just want to run through a few examples right now, like a practical scenario where can you figure out from the scenario, what's the likely parameter of interest? Is it going to be this or this? So this first one, got a survey, you took a survey of 100 college students and you asked each of them how many hours per week they spend on the internet. What parameter were you interested in? Was it a mean? And if so, what mean was it? Or was it a proportion? And if so, what proportion was it? Well, the way to analyze this kind of thing is to look at, what are you actually asking the people in your sample for? And this time you're asking them for a number. Like, somebody might say 3 hours. That's how much I spend. Another might say 5 hours a week. Another might say 2.78 hours a week. They're answering numbers. So probably you're interested in the average of numbers. Probably you're interested in a population mean mu. Once you've decided that, you want to define what mu is. You're not going to be able to say what it is as a number because you don't know it, but you can define it conceptually. And you would define it as the mean number of internet hours per week for all college students. The word all is really important there because you're stressing that this is not just what you see in your sample, it's this unknown mean for the whole population. Let's try again. In this, you've done a survey. 100 college students were asked whether or not they cited information from Wikipedia in their papers. This example, I think, is actually straight out of the textbook. What's the likely parameter of interest? Okay, this time, the question you're asking them is the kind of question that doesn't give numbers. They are going to answer yes or no. They could either say, yes, I cite information from Wikipedia when I write an essay, or no, I don't. So probably what you're interested in doing is figuring out the proportion of all college students that cite from Wikipedia. You just need to define that population proportion. And you just say the proportion of all college students, to indicate it's a proportion out of the population, who cite from Wikipedia as part of their papers. So the basic idea is, if you're asking them yes/no questions, you're probably interested in a population proportion. If you're asking them for numbers, you're interested in a mean. When you're analyzing data and looking at studies, you're looking at studies that people usually have already done. And so you're trying to figure out what it is that they were interested in. What parameter did they want to know? Because then you'll know what kinds of statistical analysis they needed to do. And then you can see whether they did that or not. One more try. Got a survey, 100 college students were surveyed. Each one of them was asked, what percentage of the time you spend on the internet is part of your coursework? So like taking all the time that you spend on the internet, what percent of that time is coursework time on the internet versus like, just playing around on the internet? So somebody might say 20%, 20% of the time I'm doing my coursework. The other 80% of the time I'm just fooling around. Another person might say 75%. Another person might say 53.23%. What's the likely parameter of interest? A lot of people are tempted to say proportion here because they think of percents as proportions, and they are, but the key is that the question you're asking them solicits a number: 83%, 27%, 52.7%. So the parameter of interest was probably a mean. The mean of the percentages of time spent on the internet that's part of coursework for all college students. Everybody in the population has their own percent, some number between 0 and 100. Average those percents, divide by how many people in the population. That's the mu that you're not going to be able to know because you can't consult everybody in the population, but it's what you'd like to estimate from your sample. So I'll say again, in this chapter, we're mostly going to work with one population proportion because that's actually related to stuff with binomials that we know a lot about. And we'll leave the other four of the big five parameters for treatment in later chapters. We'll also circle back and do a lot with one population proportion. But in chapter 5, they just want to give you the basic outlines of how you do inferential statistical work. And so they choose one parameter to do that all with. So let's get into it. The first thing to understand when you are working with a parameter that you want to know is really the variability in your estimate for that parameter. And so section 5.1 is just about that. For a proportion, when you estimate it with a sample proportion from your sample, how much variability is in that estimate? So to get an idea of how this is going to work, we need to put ourselves into a situation where there's a population that we do know everything about, so that we can watch statisticians sample from that population and see what happens to their p-hats and see how they vary. So there is an imaginary population I set up in the TigerStats package called ImagePop. So I'm going to go ahead and get some help on it and view it. So I'm going to go to my console and run help and view. And it takes a wee moment because of the other class. But ImagePop pops up after a while. And there's some help over here to help us out. Every row is an imaginary person. And there's 10,000 of these rows. You can go all the way down. Whoop, 10,000 of them. And for each person, we have recorded a sex, female or male, whether or not they're a math major, yes or no. So we got a couple of categorical nominal variables. We got a numerical variable, your income, in the annual income in dollars. CAPPUN. So CAPPUN is short for capital punishment. And you've asked each person, do you favor capital punishment? And they either oppose it or they favor it. So nice nominal categorical variable. Height in inches, numerical. Ideal height, numerical. The difference between the ideal and the actual height, so like 65 minus 63.8 is 1.2. That difference, another numerical variable. Oh, and here's a final numerical variable, k-car-temp. I better look on the help, see what that is. Oh, k-car-temp, your feelings about Kim Kardashian on a 0 to 100 scale. where 0 is very cold and 100 is very warm. So if you like totally hate Kim Kardashian, you'd give a 0. If you totally loved her as much as possible, you give 100. I guess if you were indifferent, you'd give a 50, but you could give any number from 0 to 100, and people seem to give these numbers. And I'm looking at them here, and they seem like some of them are really low, they hate her, and some of them are pretty high, they love her. I'm not seeing much in between right there. Funny, let's give this a try. GF underscore density, twiddles K car dash temperature, K car dash temp. Did I spell it right? Yep. Data equals, data equals image pop. And why don't we give it fill equals a sky blue, because I like that color. And let's just see what we get for a density plot. Oh yeah, so indeed, it seems like people either love her, because there's a mode here, and or people hate her. There's a mode here. This is very bimodal data. Very controversial figure in this imaginary population, I guess. Oh well. So that's ImagePop. And I'm going to focus in on CapPun, because that's a yes/no kind of question, you know, 2 possible options, oppose or favor. So let's just give ourselves a research question. What proportion of people in the population favor capital punishment? Okay. So the parameter that we're interested in is, you know, one population proportion. And what we're going to do is we're going to watch as statisticians take random samples from this population, and as they compute the sample proportion for themselves. So when we watch these statisticians, each of them is going to be computing a p hat. They're going to be taking their sample. They'll count the number of people in the sample who favor capital punishment. That'll be a success for them. They'll divide by the sample size, and that's going to be their p hat. And I will just point out that the number of people in the sample who favor capital punishment is actually a binomial random variable. It's got n trials, 1 for every person in the sample, and the chance of success is this p here, the proportion of all individuals in the population who favor capital punishment. It's like the Donald Trump thing that Luke just asked about earlier, you know? It's exactly the same kind of thing. So actually a sample proportion is really a binomial random variable divided by the number of its trials. It's good to know. So how are we going to get this watching of statisticians to happen? There's this function called prop sampler. And if you enter the categorical variable that you want to watch and the data set where it lives, then you can watch. So let's do this. Copy, paste, run, and you get kind of a setup here. Initially, it just gives you a cue about what's going on in the population. Turns out about 30% of the population favors capital punishment. That's the height of this red bar. That's about 0.3. And it looks like about 70% oppose capital punishment. I don't know the exact figure, but I'm reading it approximately here from these bars. Now, there's a little manipulator here where you can choose what's the sample size that your statisticians are going to use. I'm going to leave it at 10. So I'm just going to like click on this bar and make things start to happen. So down in the console, our first statistician has walked up to this population and taken a sample of size 10. And it says what happened in their sample. 2 out of the 8 favored capital punishment. The p hat was 0.2. Okay. And it cues us into what the p really was. It was actually 0.298. The height of this bar here was really 0.298. And so this sample was The p hat was not that far off of the real p. The statistician will never know that, but we can see that. Let's go ahead and do it again. So I'm just going to keep clicking on this little slider. And every time I click, a statistician is going to walk up, take a sample of size 10, and show us their p hat. So this statistician got a 0.3. And the next statistician got a 0.4. And the next statistician got a 0.3. And the next statistician got a 0.3. And you're probably like, notice the next one got a 0.2. You're probably noticing that like there's a density plot that's showing up here. This density plot is a density plot of the p hats that we've got so far. The blue dot is the last p hat that we've got, the statistician who got 20%. The red line is right at 0.298, the actual value of p. And so if you just keep on clicking, you can watch these statisticians, and some of them come pretty close to the real p. And some of them get kind of an unlucky sample of size 10, and they go kind of really far from the real p. And sometimes the app gets a little hung up because of the other class doing all that complicated work with R. And possibly some of y'all are playing along and, working the app too. But over time, you get a sense that, yeah, your p hat is, roughly p, but it's give or take some. There's some variability there. And another thing I'm noticing is that there seems to be a bit of a right tail to the density plot. Okay. Let's arrange to have our statisticians take bigger samples. How about 110? Let them take random samples of size 110 from this population. So I'm going to click. And actually, just moving it up to 110 actually got me a statistician to take a sample of size 110. It's over here in the corner. This one got a p hat of 0.24. Let's click and take another. This one got a 0.27. Then somebody came along with a 0.29 and a 0.3 and a 0.28 and a 0.34 and a 0.28 and a 0.25 and a 0.35 and a 0.2. It just goes on and on. And so as you make a statistician walk up and take a sample size 110 and show you her p hat, you notice that again, the p hats are going to be around p, but give or take less than before. The give or take figure is less when the sample size is big than when it is small. That kind of makes sense. It should be that way, because if you got a bigger sample size, you got a better chance that your sample is a representative cross-section of the overall population. And so your p hat would be closer to your p. That's kind of the idea. Another thing I'm noticing as I go on is that the right skewness doesn't seem to be as much pronounced here as it was back at sample size 10. So there's a lot of important stuff that you learn playing with this app, and I recommend that, when you're working through the screencast, you give it a try yourself. One thing we learned is that p hat is just not going to equal p, hardly ever. It's going to be around p, give or take some for chance variation in who gets into the sample. The other thing we learned is the bigger the sample size, the smaller that give or take figure was. But also that if you put the p hats together, if you put a lot of them together, you got a sense of the distribution of this random variable p hat, and it actually looks roughly bell-shaped, especially at the larger sample size, and that it's centered around the unknown population proportion p. So, when you're a statistician and you're taking a sample, you're not going to know if your p hat is close to the p or not But you do know the theory that people know by working with apps like this and doing math. You'll know it's probably close to P, and you'll even have a sense of like how close it might be. If you know something about that give or take figure. And that's what I want to get into next. Standard error. Standard error for a point estimate is just the same thing as standard deviation of a random variable. When your random variable is a point estimate, like an X bar or a P hat, then they call the standard deviation, they call it standard error. It's just another term that's there in statistics that people were used to using. And the way you should think about it is that you take a point estimate, you can think, you know, the parameter, which I don't know, is probably about equal to my point estimate, give or take a standard error or so. So it'd be really nice if you could find the standard error for your point estimate. And guess what? There's math formulas. Mathematicians have shown that the standard error for the sample proportion, the standard error for P hat, is the square root of the population proportion P times 1 minus P divided by how many people you're actually sampling. Which is cool, except that if you're a statistician, you don't know P. So you actually cannot use this formula. So what you do when you're a statistician and all you got is your sample is you say, well, you know, I was hoping that P hat was going to be around P. So I'm just going to put in a P hat here instead of a P in both those places. And maybe that'll be approximately the standard error for P hat. And it actually works out really well. P hat doesn't have to be all that close to P for this to be pretty close to the real standard error. So people do this all the time and they're fine with it. So like, for example, think back to Math 111 survey. That had 71 people in it. Sample size N was 71. Say that one of the reasons for doing the survey is that you wanted to be able to estimate the proportion of people at Georgetown College who are females. Well, then you could just use the sample proportion from your sample. You could find the proportion in your sample who are female. Now, there's various ways to do this. Like you could go to RStudio and you could say, I'd like to tally up the sex variable in the M111 survey. And it says, well, there were 40 females and 31 males. Okay, so 40 divided by 71 would be my sample proportion of females, 0.5633803. If you want to learn another R command, there's actually a function called prop. And if you do twiddle sex data equals M11 survey, it'll just figure that out for you. But once you got it, however you got it, you can go and grab the standard error. You know, you could run over and you can say, all right, I've got this 0.563303. I've got that already. Here it is. I'm going to copy it. And then I'm going to do square root of the P hat. So I'll paste in that P hat times parenthesis 1 minus, then paste in that P hat. And then inside those parentheses, I say divide by 71. And I get about 0.0588. So I could just use R like a calculator like that. And that calculation shown here, and it rounds off a bit to about 0.059 or 0.06 if you like. And so what you can say to people is, all right, I don't know the proportion of all Georgetown College students who are female. I don't know the percentage of all Georgetown College students who are female, but I got the sample. And based on my sample, I say that that percentage, that unknown percentage, is about 56.3%. give or take 6% or so. So you're just saying the unknown P is about P hat, give or take a standard error or so. That's how you're always going to think about it. The unknown parameter is about equal to the point estimate, give or take a standard error or so. So it's really a lot like talking about means and standard deviations from way back. So this is just a little review of like how, like, if you have it all in a data set, you can make R find the proportion for you. Or if you don't have it all, if you don't like want to use prop, you could actually make R like find out how many people there were in the sample just by asking for the number of rows in the data set. And then, you could work this out like a calculator. Now, sometimes in actual problems, they'll just tell you straight out how many people in the sample said yes, and they're going to tell you how many people were in the sample. And so all you would have to do is divide. You're going to see a lot of problems like that, where they'll say like 237 people out of 1,343 like Donald Trump, and then you can find the p hat. So given that the parameter ought to be roughly your estimate, give or take a standard error or so, then a concept of surprise is possible. Do you remember z-scores? I hope so, because you turned in a DA 4.1 that included them. So a z-score was value minus the mean for the group divided by the standard deviation for the group. And like, you would be surprised to learn that somebody's more than 2 standard deviations away from the mean for their group. Well, there's something similar for parameters and point estimates. As a rule, we would be surprised to learn that a parameter is more than 2 standard errors away from the point estimate. Now, I want to back that up later, but I won't fully back it up today, but I do want to introduce it. And let's just actually compute a couple of examples. So like the Georgetown College students and female, question. You were using the sample of size 71, and you got a 56.3% as your point estimate. But suppose that the registrar comes along and tells you, hey, I actually keep a list of all the students at Georgetown College, and I just computed with that whole list, and it says 60% of all Georgetown College students are female. Would you be surprised to learn that, given what you had in your data? Well, what you do is you compute a z-score off of your point estimate p hat minus this p that you've just learned divided by the standard error for your p hat. So 0.563 was what you got. 0.60 is what the registrar says is the actual value of p, and the 0.059 is our approximation for the standard error of the p hat. And it turns out you get minus 0.63. So the p hat is less than a standard error away from the p. So you would not be very surprised to learn that 60% of all Georgetown College students are female. You kind of expected your p hat to be off by a bit. But what if the registrar came along and said 70% of all Georgetown College students are female? Then you could compute that. And now the difference on top is bigger. And it actually works out now to minus 2.32. And you'd be going to the registrar and saying, wait a minute. I took a sample. And if you're right, my sample gave me a sample proportion that was more than 2 standard errors below what you're saying the P really is. Like you might be kind of dubious. Is the registrar maybe mistaken about this? Were they looking at the wrong list? Because if they're right, then something that was really unlikely to happen happened to you when you took this sample. Like maybe the registrar is wrong about it, you know. So that's the kind of feeling you'll have if you get a really big z-score. And I'll try to back that up with some probability talk later on, maybe on Thursday, we'll see. But to do that, we would have to talk about the central limit theorem, the actual shape of the probability distribution for sample proportions. And I think that would be best to do Thursday. But between now and Thursday, totally get with it. Like just go ahead right now and go to files, // Dr. White stuff, Math 111 DA. Open up that 5.1 DA, file save as, .. twiddles, double click submit, save. And, you know, between now and Thursday, work the screencasts and the slides for 5.1. Do this DA so that you can be asking some touch-up questions about it. And we'll deal with those on Thursday. And also any kind of last review or questions you might have about the quiz on Friday. That's about all I had in mind for today, and it is 3:16, so it's actually time to leave. I am going to stop the recording.